accordingly. Thank you. All right, 1.6. It's called a library of parent functions here. This is kind of the main functions we use. So 1.6 is just introduction to all of them. Some of them you've probably seen in Algebra 1, but it's introduction to all many functions we use. 1.7 is we're going to actually start moving them around. So to the right, to the left, we're going to expand them, stretch them, compress them, all the good stuff here. But let's at least do the intro to them first, and it's going to be pretty quick so we can get done. Okay, all these slides, almost all these slides have this right here. Each one has a domain and range. Each one has a even or odd. X-intercepts, Y-intercepts, increasing, decreasing, constant, or any minimum or maximum. We're good. Each one of them, we're going to have that right here. So if you want to set those up, but first one's going to be called the constant function. Cool. Constant function is the first one. It's the one that stays exactly the same no matter what. We usually graph it like this. Again, this is just come straight across. Easiest function in the world. The y value is always just the same. There's no change. So domain, it stretches all the way across, right? From negative infinity to positive infinity. The range, though, is going to be just one value. We call it b. In this case, it's 3, but it could be anything, right? 4, -12, whatever it is. And you guys talk to me here. Is this an even function or odd function or neither? So even function means you can fold it along the y-axis and it goes on itself. Odd function means you twist and then you. Yep, cool. Okay. Oh. It is an even function. Any x-intercepts? Maybe, but usually not. How about this? Only. Oh, okay. Only is spelled O. Only if b equals 0. Y-intercept is 0. When is it increasing? Never. When is it decreasing? Never. When is it constant? It's constant from negative infinity to positive infinity, which is, I should mention, on the test. On the test, some people, what they did, put actually coordinates where it started increasing and decreasing. And remember, increasing, decreasing constant is just the interval, right? It's when it occurs. It's the x values when it occurs. Any max or minimum values here? None. Okay, guys, done. First one is done. We'll get more interesting. 4, 5, 6, 7. So 8. Seven or 8. 7. Okay. Next one. Something called, and tell me if I'm going too fast, identity function. Absolutely. None. There's no max or min. It's just the same. All right, each one of these are going to have the exact same thing here. So if you want to set up the next one, domain range, symmetry, x-intercept, y-intercept, increasing, decreasing, constant, min or max. Okay, happy, we good there? Okay, identity function. Let me graph it for you, and then we'll go from there. Identity function is in one single spot. It's right here. It goes up through the origin. It hits 1, 1, 2, 2, 3, 3, 4, 4, and keeps on going out this way. Don't forget to put arrows at the end of each one. I can start bugging you guys here. I'll do it last time. I'll pick two people and then whoever wants to answer. And then if we go through it again, the other person has the other next time here. So I think I start off with Amelia and Abby last time here. So Elika and Violet, all yours. Domain, anyone? Absolutely. Infinity, positive infinity, it is as any X value would work, right? Because the domain is about X values here. Landon, Noah, range, what do you guys say? How low does it go? How high does it go?
Negative infinity, positive infinity.
I agree with that. Boom. A Lily or Noah? Symmetry. Yeah, this one not even, right? Because even before we'll across the y-axis, right? Odd is kind of a little fun one here. Odd, you have to think about if you plug in a +4, it leads to a +4. If you plug in a -4, it should lead to the opposite of that one. So if 4 went, let's just say, if 4 went to 6, let's say, right? Then a -4 should go to -6. That's kind of how it works. The odd functions work. It's odd. Absolutely. Hawk and Noah, x-intercept, y-intercept.
0, 0.
Okay. X-intercept would be 0. Y-intercept is also 0. I guess it should be like this here. Yeah, it goes through the origin. And Joe and Elijah, increasing, decreasing, constant. Increasing all the way through negative infinity to positive infinity. This is none at this point, none. And is there a max or min? None. Kind of boring, guys, I gotta say. It's a little bit, maybe towards the end of the interest here. Okay, sometimes this is actually mixed up with the linear function, but the identity function always goes right to the origin. We good? The coordinates are always the same, -3, -3, 1, 1, 7, 7. Now we have the linear function. Okay, tell me if we need to go back. Let me write. Linear function. Now I can draw this anywhere I like. So I'm going to go maybe like this right here. That's fine. Boom. That's a linear function. It does have a formula. Y is equal to mx plus b. Cool. Do the other stuff with it or not? Okay. So you can draw this anywhere you like as long as it's a line. Linear equations here from negative infinity to positive infinity. You can plug in whatever you like. Range, again, same exact thing. Linear functions don't have to be even or odd. They could be, but for the most part, they're neither. Okay, so there does exist an x-intercept. Yes, that's true. Most of the time. We just don't know what it is. There's no formula for x-intercept. For the y-intercept, yes, there is a formula. It's y is equal to b. There's your formula. And when is this increasing? This is increasing if the slope is greater than 0. It's increasing when the slope is less than 0. And a constant function when the slope is 0. That goes back to a constant function. almost halfway done. And then we'll go into something different. Okay, do good. This is called the quadratic function. Sometimes actually called the squaring function. All right, I can draw this anywhere I like. I can draw it over here, I can draw it over here, but anyways, essentially does something like this. Bless you. Oh, sorry. Sorry. The specific formula to it is just x squared. There's your squaring function. It goes like here, and then it comes back up. There's your squaring function. Jam, let's go through it again here. Amelia, Abby, which one? Domain.
Does it go straight off of the X, or does it continue going?
Continue goes sideways a little bit. Yeah, it just goes. Yeah, it just goes more and more steep, but it still keeps on going here. Elka, Violet, range.
Here it's all positive, but
Uh-huh. I don't see any graph here though. That's my little issue as I kind of scan as I go up. It goes up to positive infinity. Absolutely true. Here is there a bottom to it?
not here.
Ah, okay. Real quick here. Sorry. So this is quadratic function, but it's specifically this function right here. It's specifically the x squared function. So if it's x squared, the lowest it'll go is 0. Is that right? So in this case, 0. Does it include the 0? Does it actually touch 0? Oh, sorry. Okay, boom. It does touch 0, right? It's actually hits 0, 0. So in this case, you do need a bracket 0. 0 to infinity. It is even, absolutely. X intercepts, yes, x equals 0. Or you can just say 0. It hitting at the origin. Increasing from negative infinity to positive infinity. Is it ever constant? None. Decreasing. Oh, sorry, guys, sorry. I'm going a little too fast. I should go like this here. Let's go Landon, Noah. Increasing.
Yeah.
Where is it increasing? What interval is it increasing? So you're just looking at the slope going down, then turning around, going up. And so when is it increasing?
Is it negative? Or is it 0?
Ah, cool. So it's increasing, starts increasing right here, right? That's when it starts going up. So absolutely. And then with increasing, you don't ever put brackets. You always put parentheses because it's always beyond that. It doesn't ever increase at that point. So 0 to positive infinity. Boom, Lily or Noah, decreasing. And there's still a parenthesis around 0 because with increasing, decreasing, you're always thinking about what's happening in between 2 points, not at a single point. So you don't ever include that here. So I'm going to go none and Minimum or maximum? Yes. There's a minimum at 0, 0. Okay, quadratic function or squaring function. And we can start moving this around to the left, to the right. We can start flipping it around. That'll be 1.7. Everybody good with this one? 3 more to go, guys. 3 more to go. Not the funnest thing in the world. I mean, you for sure know it's not the funnest thing in the world when Joe starts singing. So a cubic function. Cubic function looks like this. It's x cubed. And there's, maybe I could just draw a little bit better here. So I know it goes through 0, 0, no, 0, 0. Goes through 1, 1. By the time you get to 2, it's all the way up an 8. So it goes up quickly. -1 times -1 times -1 is -1. -2 times -2 times -2 times -2 is -8. So it kind of goes like this. It goes down this way. Comes back up. There's a kind of like slight little turn here. And then turns again. And then like that. Boom. Noah, sorry, Luke and Hawk, all yours. Domain and range. There's, boom. Luke, all yours. Range. Range is all the Y values that work. And so this case, it's looking down low. It goes down forever. And then, absolutely. And Elijah and Joe. Symmetry, even odd neither. I'll give you a hint. It's 3 letters. Odd. All right, that's perfect.
Wow.
Awesome. Because notice what happens with a positive one, it goes up to 1, and with the negative one, it goes to -1. So the signs switch. 2 goes up to 8. So -2 goes down to -8. So the signs switch as you go. X-intercept 0, Y-intercept 0, because it is in the origin. And Abby, Amelia, increasing, decreasing, constant. Those 3.
I have a question.
Sure.
Domain and range, does it turn into a strictly vertical line, or does it still continue?
No, still continues going sideways, just slightly. It goes up fast though. Goes up super fast. You're trying to divert me. It is always increasing. Yeah, it starts very low, right? It just kind of keeps on going up and up and up. There's maybe like, doesn't even pause at 0, 0, right? It just kind of keeps on going, goes through 0, 0, keeps on going here. So increasing infinity to positive infinity, it is always increasing. That means there's no other interval that it could do anything else. And because it's increasing always, it's also a none as well. 2 more, guys. 2 more to go. Let me just check something real quickly here. Yeah, I have it. All right, so we have the squaring function, we have the cubic function. So let's go the other way here. We have the square root function. Formula looks like this. Square root of x. And let me do something really quickly here. I'm gonna go here. Give myself. Oh, I did already. Okay. I got myself extra sheets because I wanted in. do the other ones here. Boom. Okay, what does a graph of this look like? The square root of x. It starts off at 0, 0. It goes through 1, 1. Then it goes through 4, 2. Because the square root of 4 is 2. And then it kind of keeps on going like that. Alka, Violet, all yours, domain and range. Perfect. Zero positivity. Does it include the 0? Does it actually hit 0? Like, can you plug in a 0 into that function? I think so, yeah, huh? The square root of 0. Yep. So it's a bracket. Bracket 0 to positive infinity. Violet range. What do you say?
The same thing.
Same thing. Hits 0 and keeps on going. Landon, Noah, even, odd, neither. Neither, yep. It doesn't fold across the y-axis, or it doesn't change signs here. X-intercept, I'll do this one. X-intercept to 0, y-intercept to 0, perfect. Lily, Noah, increasing, decreasing, constant. Just increasing, huh? Yep. So with increasing, again, always a parenthesis for increasing, decreasing. Decreasing, none. Constant, none. And is there a minimum? Minimum at 0, 0. Okay. I'm not sure why the book does not show you this one, but we should know this one too here. So this is the square root function. Since we did the squaring function, we should go the other way too here. So this is called the cube root. The cube root function. All right, let me graph this guy here. This is -1, -1. Let's see, cube root, -8. -8 goes down to -2, so it's like right here. Thank you for reminding me here. It is a little 3. We'll call this little thing called the index. The 3 is the index here. Okay, so 1, 1, and then all the way out to here. So it goes like this, kind of comes up like that, goes through 0, 0, hits 1, 1, and then curves that way. Phew, this one and one more. We'll get through all of the parent functions. No, it should be curved. Yeah, it should be slightly curved like this, like it is on top. If you want to redraw it, it kind of, it's just.
So this was the same thing as a cubic function, but sideways.
Absolutely. I'll get that again. All right, the book doesn't have it as one of those parent functions, but it is. You know, just author, I don't know what he did. Fell asleep for a little while. Forgot about it. Hawk and Luke, all yours. Domain and range. Luke. Awesome. Yep. Because it's going to go up forever, goes down forever. Joe and Elijah, even, odd, neither. It is odd now. Yep, absolutely. It is absolutely, it's odd. Because the positives switch into negatives. X-intercept, 0. Y-intercept, 0. Done. Amelia and Abby, increasing, decreasing. Or constant. It's increasing. Isn't that kind of crazy? I think it's kind of funny the fact that something can be increasing forever. Okay, none on these guys, none on these guys, and then none for this one as well. Phew, finally got to the last one here, or maybe second to last one, the last one that we have to deal with here. Thanks for being patient. I know not a fun lecture to look at stuff. We've got to get through all of these here. Okay, last one of this kind here, something called the reciprocal function. Reciprocal function, f of x is 1 over x. This one, what we do is we put actually dashed lines right along the y-axis. We put dashed lines right along the x-axis as well. And this graph goes like this. It goes this way and then goes right through -1, and then bends down this way forever. Comes back down, 1, 1, 1, and then turns and then goes like this. Okay, let the fun begin now. Not sure where we left off. Elica and Violet, all your domain and range.
Sorry, Mr. Chairman.
Yeah, no problem. That's a toughie, huh?
Yeah,
So you're sweeping across from left to right. And the question is there always a graph or is there a break anywhere?
there's a break.
Yeah, there's a break. There's a break right at 0. Absolutely. So we have a function. Everything's fine from -infinity all the way up to 0. And then right at 0, there's that little dash line comes down. There's your break. Then it starts back up after 0 and everything's fine.
Is it in the middle, when x equals? I guess x equals 0.
X can equal 0 because remember we can't divide by 0, right? 1 over 0 is nothing.
So another point equals 0.
Correcto. So this is one of those, Abby, where you're saying like, does this ever go horizontally straight up? Still no. Even though there's a border, it still etches closer and closer to the border each and every single time it goes up. So there's never time to go straight up. By all yours, range. Range is now you're looking from bottom to top.
Wait, so wouldn't it just be the same as the domain?
Absolutely, yeah. Everything's great here. You got a graph here, got a graph here, got a graph here. When you get to this one single point right here, you don't have a graph. So -infinity to 0 is fine. Anything above 0 is fine as well. Noah, Lyndon, even odd neither. Odd is cool. Yep. You notice the little sign changes, right? 1 goes to 1, -1 goes to -1. Technically 2 goes to 1/2, so therefore -2 goes to -1/2. Lily and Noah, x-intercept, y-intercepts. Absolutely can't be, right? Because the dash lines across the y-axis, dash lines across the x-axis, and this guy there is none. None. Hawk and Luke, increasing, decreasing, constant. It is not increasing. Absolutely. This guy goes down, 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 down. Then it jumps and it goes down, 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 down again forever. So not increasing, none. Decreasing? I think so. All the way from -infinity all the way up to 0. Then we have that little break. And then after that, 0 to positive infinity. Notice it's just the interval that it's happening, right? None here and then none again. Okay, I find this kind of crazy, especially math. So you have this guy here, right here on the side. This guy's going down. This guy's going to go down forever and ever and ever. Yet it never touches x equals 0, right? Just gets, but it still is going down forever. And so you got this whole concept of the first time this was actually introduced was in the Greeks. And this was called Zeno. Yep, his name was called Zeno. Zeno's paradox. So he talked about this interesting concept. If you have Stickman over here, and he's trying to reach the wall. Yeah. In which geometry class, I assume?
No, logic class.
In logic class, gotcha. Okay. So if every single second, so every single 1 second, this person here goes half the distance to the wall, right? So 1 second here, then the next second, this is second number 2, then second number 3, all that stuff. And how long was it going to take him to get to that wall? These deck are going to make it.
Just conceptually, but in real life, you will reach the wall.
Absolutely. So like in the chemistry class, right? Like chemistry, technically, we don't, did you guys know this? We don't ever touch anything, right? But then in real life, we do, right? So if you ever get into a fight next time, you just said, never hit him.
The only way this would work is if every time we did it, you just swapped it. Because that way you would never cross the wall. In real life, you would just run out of being able to step the time you're trying to distance.
Uh-huh. Very true, yeah. So sometimes things aren't the way reality is sometimes in that way, or view reality differently.
I heard another logic puzzle that's similar to this,
Uh-huh.
and it's that there's an ant on an ever expanding rope. So at first it starts out 1 inch long, and every minute it doubles the length.
Oh, wow, okay.
So, or every second it doubles the length, whatever you want to say.
Uh-huh.
But eventually the ant will reach the other side because it's the rope is stretching underneath it, so it's staying in the same place, but there's distance being gained by the stretching.
Interesting. I have to think about that. Think about that one here. Okay, so what do we do next? Is we define a piecewise function here. Piecewise. P-I like pieces. Piecewise functions. What do we do here is we're going to start combining functions together. So let's do one like this here. So example number 1 would be good. F of x is equal to x squared for any x's that are greater than or equal to 0. And the absolute value of x for any x is greater than 0. So absolute value is still not considered not even in the book, but absolute value should be considered a parent function. It just didn't happen here. Okay, guys. Can you graph this? Can you graph this function? Oh, sorry, hold on. Less than equal to 0. There it is. I should graph it. That's why I did it. Okay. One second, class. Let me just move things around real quickly. I wanted one of these graphs. That's what I wanted. Copy. Paste. There it is. Okay.
Wait, wouldn't it actually be the opposite way around, where x squared is only when x is greater than or equal to 0, and just logically you have the absolute value of x that would only be really necessary if we want.
True. Yeah. So in this case, absolute value of x is not really necessary. You could have just put x if you wanted to, right? But we're trying to combine two functions. I did want to show the absolute value function here too. So all yours, if we were to graph x squared, right? X squared would look like this. It's 0, 0, negative 1, 1, 2, 4, and we keep on going. 3 goes to 9. So I got a function that looks like this, comes down, But when it hits 0, 0, there's my x squared function, right? What happens after 0, 0? Absolute value of 1 is 1, absolute value of 2 is 2, so it becomes a straight line afterwards, right?
Wouldn't the increasing part of it be on the other side of the line?
Talk to me. Go ahead, say again. So half of it is a square root function, right? Half of it is a absolute function. It's kind of like from Batman, it's Two-Face. So it goes one way, then goes the other. Okay, so what we're doing is we're just combining these functions together. We're good into different pieces. We can either draw it out or we can do the other way, which is example number 2. Sorry, 1 second. I am off a little bit here. Let's see what I'm doing. Oh, sorry. 1 second, class. Before we get there. My slides are off. 1, 2. Let me check one thing real quickly here. Oh yeah, this is the way I want to do it. Okay, it was out of order. This would be exercise number 2. It's out of order. Let's go the other way. Can you guys write for me the equation of the piecewise function?
Yeah, but if I was smarter, probably.
So think of this little function. What does that function look like?
Hang on, I'm putting it back to you. It looks like the quadratic form.
It's a quadratic function. Okay, so piecewise function, I go f of x equals, thank you, Abby. Boom. The quadratic function, which is x squared. And then when is this used? When is the break in our graph? It's at 1. It occurs at x equals 1. It's like right here, isn't it? There's when we switch graphs. That's when Two-Face turns. How's it 1? It's just, oh, sorry, 2. I'm sorry. You guys are right. It's at 2. So the change occurs at x equals 2. So we use the x squared function for anything up to, oh, here it is. It was a 2, 4, 6. Sorry, I thought it was a 1. 1 is over here. This now is 2, 4. Okay, guys, real quick here. Let's think about this here. Open dot, close dot. Have you guys seen this before? Yeah. Which one has the equal sign with it? Is it the x squared or the other function? Yeah, the closed dot means that graph has that point. We're good? The open dot means anything above that point.
So in this case, that means that they are completely separated.
So that's why we do need the open dot, closed dot, because open dot, closed dot tells you which one has the point. So are we okay with x is less than or equal to 2 for the square function?
Oh wait, isn't it? It's really hard to tell from here, because it looks like it ends almost at 3, between 2 and 4.
It ended like, well, no, it ended, yeah, it does look like it ended 3 because they opened dot.
2. Put in a 2. But yeah,
No, but keep going up, right there, it continues going up.
if it keeps on going up, it would be somewhere like right here, wouldn't it? Something like that.
4.
We'll have to see. I don't know. I have to get the equation this line now. So this is a straight line. I know this is going to be y equals mx plus b, right? Question is, do you guys know the slope?
Oh, absolutely.
It's the absolute value of x.
What you said.
It was the vertical amount times the absolute value of x.
Absolute value would be going up, not down.
Negative x plus 6.
Okay, and Noah says negative x plus 6. You guys agree, disagree?
Sounds great.
Sounds great. Okay, let's go with it here. So if you're at 3, we're going to go to 7. So that means we go 4 over, right? 1, 2, 3, 4. and we go 4 down, 1, 2, 3, 4. Everybody good? That's
Plus 7,
4 here, minus 4.
negative x plus 7.
3 down?
No, it was before.
Oh, no, you're right.
Just trying to get the slope. We good?
I was looking at the wrong one.
It's
Oh,
x
yeah,
is
yeah,
plus
yeah.
7, I believe.
Right? It's 4 over, right? Going from 3 to 7. And then it is going 4 down. So -1 is the slope. -4 over 4, m is equal to -1. Cool. Now the question is, when does it hit the x-axis or the y-axis? Is it 6? Is it higher, lower?
7.
7?
Approximately.
So if it goes backwards here, can be approximately. If it goes 1, 2, 3 to the left, that means it'll go 1, 2, 3 up. That's 7, huh? Okay, so 6 changes into 7, and there's our other formula. Y is equal to -x plus 7.
Well, I
When
saw
does this-
7 comma 0, and that's where I realized, that's when I realized that it would have to be 7.
Gotcha, because the slope of -1, it goes through 7, 0, therefore it's going to have to go through 0, 7. Perfecto. When does it work? X is
Greater than or equal to 4.
so.
No, sorry. 4.
So everything is dependent upon this little 2 right here, right? It's where it works, not the y value, just only the x value.
So I guess it's 3.
No, it is just 2. Everybody okay with 2?
Yeah,
Right.
those two graphs are supposed to be connected.
They are not connected, but they change. They change right at x equals 2.
Okay.
Okay, guys. So all the different parent functions. Say again.
It's making a lot of sense now, but I can tell I'm gonna go home and start the homework and just be like,
That's okay. Come back with homework questions. So got all the parent functions here. We put them together as pieces now. We good that way? One more thing we got to do. One more introduction to stuff. This little guy right here. So this would be example 3. One more weird function. This should be example 3. And I got them out of order here. Oh, okay, absolute value of greatest integer. Okay, there's 2 more at the end. So that's right. The book, what does the book do? The book introduced the absolute value function all at the end. Okay, guys, real quick here. Funny notation. You guys ready for this? Looks like a bracket, but there's extra bars coming down. There you go.
Brackets around the absolute value.
So bracket bars. I guess we should say it like that.
Oh, wait.
Okay, what in the world is this? Just real quick here. This little function, it means the biggest integer up to that point. So let's do this here. So if I were to do this, let me, real quick, don't write this down. Just kind of, you can if you want to. What is the greatest integer up to 1.5, but not going over? Greatest integer. Just 1, huh? 1. Everybody good there? So if I go 1.9, greatest integer up to 1.9, but not going over. Still 1. Greatest integer up to 1.999 without going over. 1. Greatest integer inside 2. 2. Greatest integer inside 2.1. Okay, 2.1. Still a 2. Are we good there? Awesome. Okay, so it's the greatest integer up to that point, but not going over. Where is this used at? Stamps is one way it's used at, right? If you have a certain amount of packaging, if it's under so many ounces, it's one price, and then each time it jumps. So each time it jumps an ounce, it jumps in price. And the graph of it kind of looks funky too, which we'll graph in just a little bit as the last thing we'll do. Okay, so let's do this here. Let's graph this guy right here. One last one. So, so on your notes here, if you want to put example 3, put f of x is equal to greatest integer of x plus 1. That's what we'll do. It's also considered a parent function, just not very used. I mean, not very used in algebra, but used a lot in other places. Okay, so let's go with it. We're gonna have to draw this function out. It says try at least put in these values here. That would help. So if you put a -1 into here, -1 plus 1, oh sorry, absolute value of greatest integer inside apps is -1, still -1, -1 plus 1, 0. So -1 is going to graph at 0 with a closed dot. We good? Everybody okay with the closed dot there? Okay, if you graph 2 inside here.
Oh, no, yeah. I was like, you're supposed to add.
Plus 1 is just adding 1 to it. 3. So 2 jumps to 3. Okay, that's cool. And then how about 1.5 or 3/2?
2. It comes to 2.
2. And so that one is 1.5, jumps to 2 right here. Okay. So then let's fill in the rest of them here. So how about f of 1.9?
Shouldn't that first dot have been a 0?
Wait, the 1.5 is not 2. No, it is 2. I forget that one.
The 1.9
Sorry, Abby, you saying for the first one?
That first dot that's on -1, shouldn't that be on 0?
So -1 is on 0 along the y-axis.
Oh.
Okay, let's finish this up here. So 1.9 is about right here. Still 2, right? 1.99,
Look at
2.
-1 gram on
1.999999.
your postage stamps that you don't have to pay.
Still 2, right? Let's finish up. Just we have 2.5 minutes left here. So 1.9 is still 2, but then when you hit 2, it jumps. So what we're going to do is we're going to put an open dot right here. We're good. Let's go back up to negative. Let's go back down to -1. -1, -1/2.
That would be 1.
No, it'd be 0.
-1/2.
Sorry, I misunderstood what you were saying. Yeah.
Uh-huh. Well, okay, let me graph the positive side here. So if you plug in a 0 into here, it'll be a 1, is that right? A 1/2 would still be 1. 0.9 would still be 1. So it has a closed dot here, and it goes, and has an open dot right here. At 1, it's going to jump to 2, closed dot, and it keeps on going all the way to the next one. Then jumps, keeps on going to the next one with the open dot, and then you're going to have a jump to the next one. And then how many of these do you do? Just a few, just to get a view of it. Okay, then you got to have to go backwards just a little bit here. So close, open dot backwards, open dot backwards, and last one, open dot backwards, and we are done for the day. There's the step function. All right, so you guys should be able to do the rest, all of the homework for 1.6. We finished up that one today.